Let me ask you something that sounds profoundly simple, yet will stick in your head all day once you hear it. If you climb a mountain, you are, mathematically speaking, getting closer to the sun, right? So, why does it get soul-crushingly colder up there? Seriously, shouldn't it be the opposite? You're gaining thousands of feet of altitude, moving straight toward that colossal, fiery star that blasts Earth with energy 24/7. That blinding sunburn you got last summer, that heat traveled 93 million miles. So, climbing a few miles higher should feel like moving a little closer to a roaring bonfire. And yet, the higher you climb, the more it feels like someone left the door open on a cosmic freezer. Meanwhile, back at the beach, people are sweating through their shirts. Why does closer to the sun not mean closer to warmth? The answer flips everything you thought you knew about heat upside down. Most of us have a simple, intuitive understanding: the sun heats the air. But here is the massive plot twist that changes everything. The sun's energy, arriving as visible light, is actually terrible at heating the air directly. Sunlight passes straight through the atmosphere and slams into the Earth's surface, the ground, the pavement, the vast oceans. That is what absorbs the energy. The ground then becomes an oven, re-emitting that stored energy back up into the air as infrared radiation, or what we call heat. It's like the sun sends a package, and the Earth's surface is the only thing that knows how to unwrap it and share the warmth. So, at sea level, you're standing in a thick, cozy thermal layer of air that's being cooked from the bottom up. When you climb a mountain, you are simply moving away from the stove. Let's put the concept of closeness into perspective. Mount Everest is about 5.5 miles tall, while the sun is 93 million miles away. Standing on the summit gets you a minuscule fraction closer to the sun than if you were at sea level. That is less than 1 inch closer to a bonfire across an entire football field. Being closer to the sun does absolutely nothing to help you feel warmer. What actually matters is how well the environment around you holds on to that energy once it arrives. And mountains, as we will see, are incredibly bad at holding heat. The first major cooling force is a bizarre physical process called adiabatic cooling. As you climb, the air pressure drops significantly, and the air molecules spread out. This has a strange consequence. The air cools itself down, without losing any heat, to the outside environment. Think of a spray can of air duster. When you spray it, the can gets ice cold, right? The gas inside expanded rapidly and used up its own internal energy to do the work of expanding. That energy loss is what causes the chilling effect. This happens to every rising pocket of air in the atmosphere. As the air rises toward the mountain peak, it expands against lower pressure and cools itself down. The air at the top of a mountain is naturally colder because physics literally made it that way. The second force is the vanishing thermal blanket. At sea level, the atmosphere is thick, dense, and heavy, like a giant down comforter. There are billions of molecules per cubic inch, constantly bumping into each other, exchanging energy, and trapping heat. As you climb higher, that blanket gets threadbare and the air becomes thin. Eventually, you're not wrapped in warmth anymore, you're just exposed. The few air molecules left are too far apart to effectively share or store the heat from the ground. It's like going from a crowded party to an empty warehouse. Need visceral proof of this altitude effect? Look no further than Mount Kilimanjaro in Tanzania, which sits almost directly on the equator. The base of the mountain is tropical rainforest, hot and humid enough to make you sweat by breakfast. But climb the 341 feet to the summit, and you will find permanent snow, glaciers, and bone-chilling, freezing temperatures. Same sun, same continent, same day. Altitude is the only thing that changed. This is an undeniable demonstration that it's not the sun's proximity that matters. What matters is the density and quality of the air around you. Let's go even higher than the mountains. Commercial jets fly at around 35,000 to 40,000 feet, while above any peak. Up there, the external air temperature is typically a terrifying 60 degrees Fahrenheit. They fly there precisely because the air is so thin, which means less air drag and better fuel efficiency. But outside that tiny aluminum tube, it's brutally cold. If the cabin systems fail, You lose consciousness, and then you freeze. Even in full sunlight, the atmosphere up there is just empty, freezing space. The ultimate proof is space itself. Space is the closest you can get to the sun without actually hitting it. Still, it is cold. If being closer to the sun meant more warmth, then space should be a tropical paradise. Space is mostly a vacuum, no air, no molecules, nothing to trap heat. If sunlight hits you directly, the exposed side of your body can instantly reach 250 degrees Fahrenheit. But the side facing away simultaneously plummets to 250 degrees Fahrenheit. There is no atmosphere to distribute, trap, or share that energy. Heat needs a team. Let's zoom out for a global context. At lower altitudes, Earth's atmosphere acts like a massive thermal blanket. Sunlight comes in, hits the surface, and bounces back up as heat. Greenhouse gases, like carbon dioxide, methane, and crucial water vapor, trap some of it and radiate it back down. That is the greenhouse effect, and it's what keeps our planet warm enough for life to exist. But up on a mountain, the thermal blanket is virtually transparent. There's less water vapor, less carbon dioxide, less of everything. The greenhouse effect still exists, but it's drastically weaker. There's nothing to catch the heat and bounce it back to you. It just slips away. You can actually see this effect at work in one of the lowest places on Earth, the desert. Take the Sahara, for example, which is at a low altitude. However, it has incredibly dry air with almost zero water vapor, even though it might be a scorching 120 degrees Fahrenheit during the day. It can plunge to near freezing after sunset. Same principle as the mountain, no insulation means fast, hard heat loss. It's not just about height. It's about the quality of the air you're in. The lack of a humid thermal layer is what allows the temperature to crash. So, to answer the question, the higher we climb, the colder it gets. This is not because the sun loves us less, but because you're stepping beyond the shelter that makes life possible. Warmth is never about just being in the sun. It's about what that sunlight lands on, the Earth's surface, and it's about the support system in place to retain it a dense, humid atmosphere. It reminds us of the atmosphere that hugs us close and the oceans that cradle heat. Life thrives because of the thin, precious blanket that our planet wears. And when you leave that blanket behind, the laws of physics are absolutely unforgiving. The great heat paradox is, in fact, a reminder of the fragility of our world.